Hey, hi everyone. So today is day 11. We have completed the trees and stuff. Um, yesterday I couldn't come live, but what I did is I worked on a blog on decision tree that we have covered till now. Um, I mean, the blog is more. Uh, it's more on explaining decision tree with respect to an analogy, comparing with the war situation and stuff, and how do you deal with it and stuff. Our video has a much more detailed explanation, but the blog was also interesting. Let me share the blog with you guys as well. Is it here? Okay. Yeah, I'm sharing my screen. So this is the blog I wrote, Dictionary Anti-Intelligence Algorithm. My thinking is going saying it's little uh, it's not 100%, but I would say decision tree. If you go detail into the detail, 70% of it is it sounded like more like a brute force. It's actually 100% brute force, but 30% because of the optimization on how we pick up the features, how we pick up the values and stuff, and how we can reduce overfitting. The other things that came in, which I added a little bit of intelligence, or else for me, by the core understanding, it sounded more like a brute force algorithm. So what happened is I was actually trying to put this. Um, the initial version that I prepared, it was more draft, and I was actually going a little negative on it. So um, let's change topics. Okay, we'll publish this blog machine learning session tree and AI and hmm, in terms. Yeah, so this I okay. Let me share it on LinkedIn too. It should not ask me for login. Unintelligent. Okay, this is done. We're good. We'll get started with. Okay, I'll copy it. I'll just publish it soon. This is not good to be recorded. I'll go back to the recording. So decision tree, you guys can go through it. I'll not go through it now because it's waste of time and we don't have much time today. So um, we will today's focus will be we have completed the uh, decision tree piece part of it. I think we've explained about information entropy, information gain, Gini index. I think these are the three metrics basing on which we make a call on each of the nodes and then we build the decision trees. I also explained previously on what is random forest, what is uh, X GBM, that is extreme gradient boosting algorithms and stuff. And we understood a little bit about ensembling models and all that, right? That being done, there are few additional things that we need to understand from the core concepts piece part of it. So today we'll walk through with ChatGPT. ChatGPT says these are few things that we need to study. It recommended saying these are a few other things besides linear logistic regression, decision trees, random forest. What are the other things to do is my question, and it said we can cover support vector machines, naive Bayes classifier, K, nearest neighbors, and then these are all boosting and optimization and all techniques. They are not real. Bayesian networks is okay. That's what it said. So let's try to focus on these five things if we can cover um, as much as possible. Let's try to understand them, but I'm not gonna get to the details on derivations and how it is working and all that, as we went for linear regression, logistic regression, decision trees and stuff to the detail. But we'll understand what is what in it, because after and when the direction which we are going is generative AI and stuff, nothing wrong with these models or nothing to say that these are not being used or something. Um, these might be used by people basing on the use case. Especially people use them not today. People don't use many of the machine learning models individually for a use case. They usually use ensembling approach, and in ensembling approach where they use multiple models together, they pick up models um, of different of heterogeneous kinds, and then they try to see how it works and stuff. So they might use this for that purposes and stuff. But okay, let's go to SVM. SVM is support vector machines, and support vector machines, they cover both variants. I mean, okay, today it's more reading is what I'm gonna do. It has both regression and classification capabilities. uh, Okay, let's ask. Explain me about vector machines, how they have evolved, and why they create such algorithm even when we have linear logistic trees. So it'll explain now about support vector machines. I'll just read out what is there in the things. Support vector machines are powerful supervised learning algorithms used for classification. Again, we're still in supervised. They were first introduced by and have since become widely used in various fields, including computer vision, natural language um, processing, and bioinformatics. Also, SVM formulation for binary classification tasks and linearly separable data. SVMs aim to find the hyperplane that maximally separates the classes while while maximizing the margin, the distance between hyperplanes, and the closest data points. Okay, I mean, I think that's the key point. So, um, okay, we'll read through it and then summarize at the end instead of talking. Kernel kernel trick. One of the key innovations in SVMs was the introduction of the kernel trick. This allows SVMs to handle non-linearly separable data by implicitly mapping the input features into a higher dimensional space where the classes become linearly separable. Okay. Soft margin SVM. The original SVM formulation aimed to find the maximum margin hyperplane, which might be sensitive to outliers. The introduction of soft margin SVMs allowed for some misclassification errors by introducing a penalty parameter C, which controls the trade off between maximizing the margin and minimizing classification errors. What is margin, what is classification error is something we'll look at it, but let's understand. So, soft margin SVM, C have introduced to handle outliers. Okay. Multi-class classification. As well as initially designed for binary classification, there's other techniques like one versus one strategies have been developed to extend SVMs for multi-class classes. This is same way thing that we learned in logistic regression. We iteratively apply the model on multiple models where we say that this is apple and then we say these are other fruits, and then we take the other fruits and then say okay, out of it this is orange and remaining other fruits. So we go incrementally to do the multi-class classification, but these are not doing one shot multi-class where the output directly says what kind of fruit it is, kind of stuff. So it is like you classify as not apple, not orange, and then maybe you go towards something like it's banana kind of stuff. So that's kind of approach. SVM regressor SVMs can also use for regression tasks. SVR support vector machines became subto vector regressor. SVR aims to find a hyperplane that minimizes the error between the predicted and actual target values while maintaining the maximum margin. Kernel methods. So SVMs are closely related to kernel methods, which generalize the idea of SVMs to other learning tasks. Kernel methods use kernel functions to implicitly map data into a higher dimension space, enabling nonlinear decision boundaries. Kernel methods is something that we need to also know. So there are points that are important. I'm skipping. I'm just make a note of those. Kernel method. Okay. And what is the other things? Soft margin SVM. And kernel trick and kernel method should cover it. Hyperplane, multi-class classification, SVM regressors, kernel methods. Okay. Effective in high dimensional spaces. SVMs are effective in high dimensional spaces, making them suitable for tasks with many, such as image classification, text classification, versatility with kernel functions. It can handle nonlinear decision boundaries through the use of various kernel functions, including linear, polynomial, radial, basis functions, and sigmoid kernel. Kernel methods, kernel functions. So much is there on the kernel. We should understand what this kernel is really. Robustness to overfitting. Assumes are less prone to overfitting, especially in higher dimensional spaces, due to they're able to maximize the margins between classes. I understand maximize margins, but little bit it's better to revisit and understand. Global optimality. The SVMs aim to find the hyperplane that maximally separates the classes, leading to solutions that are often globally optimal. Okay. Effectiveness in higher dimensional spaces. SVMs are particularly effective in high dimensional spaces, which other algorithms like logistic regression may struggle to. computational complexity, robustness to outliers, due to the margin concept making them suitable for datasets with noisy or unbalanced data classes. Flexibility with kernels. The use of kernel functions allows SVMs to handle non-linearly separable data, providing more flexibility compared to linear models like logistic regression. So non-linearly separable data is handled well in SVMs compared to linear and logistic models. Global optimization SVMs aim to find the hyperplane that maximizes. The same thing is repeating. This is leading to solutions that are often SVMs have evolved to become powerful algorithms for various machine learning tasks, offering advantages such as effective handling of higher dimensional data, robustness to outliers, and flexibility with nonlinear decision boundaries through kernel functions. When they say it's nonlinear, but they pick up hyperplane, which is actually linear. I think the hyperplanes are linear in SVMs, but it's a good point. SVM hyperplane, are they linear? Good question to ask. Okay. Steps. Here are the general steps to build SVM: data cleaning, feature scaling, feature engineering, splitting the data, selecting the SVM kernel, and kernel function based on the nature of the data and the problem at hand. Common choices include linear, polynomial, radial, basis function, and segment kernels. Training the SVM model, user training, tuning, evaluation, deployment, monitoring. That is actually common. I think the whole key step is to understand about kernels. So let's understand what are kernels and how are they used in algorithms. Kernels are a fundamental concept in machine learning, particularly in algorithms like support vector machines and kernel methods. This is a mathematical function that computes this similarity or inner product between pairs of data points in a high dimensional feature space. Kernels algorithm implicitly operate in high dimensional space without input data handling, nonlinearity, and number nonlinear boundaries by implicit. Specified. Computational efficiency instead of explicitly transforming the data into a higher dimensional space. Kernels compute the inner product between data points and the original feature space, which is often computationally more efficient. Kernels provide flexibility in choosing this impact. A linear kernel linear kernel computes the dot product between the input feature vector x and y in the original feature space. Okay. Polynomial kernel computes the dot product raised to a power of d, optionally adding a constant term c. Okay. Radial basis function RBF kernel e power minus gamma of x minus y mod square. RBF kernel measures the similarity between data Gaussian or radial basis function. It's suitable for capturing complex nonlinear decision boundaries. So there are decision boundaries which could be nonlinear also in SVM. Sigmoid kernel computes the hyperbolic tangent of a linear combinations of input feature vectors, optionally adding a constant to it. I feel I should rely on watching a YouTube video as well. So what they're doing is they are applying they're taking all the data points. They, because it's a supervised learning, they know the output that is there. Basing on output that's there, they are actually so basing on the output that is there and the input combination, that's the pattern, right? Like given input, this is the output, that's the pattern, right? For the inputs, they are applying a function in a way that the those input points are are either increased or decreased in one direction related to y. So if y is some value, if the y is, let's say, 0, it goes in one direction. If the y is 1, it goes in one direction. So using that, what they're doing is that they're actually segregating the points, instead of keeping them very, in a layer, in a plane where they're all mixed up. What they're doing is they're taking them to the, they're changing the values, are are literally, they're like, they're pushing them away from each other, so that we can actually draw. The problem of drawing a line is, if all the blue points, let's assume they're blue and red dots, and the blue and red dots are already visibly separated with respect to their values and stuff, then it is very easy to draw a line in between, right? So like even the algorithm can draw a line in between. Challenge comes is where they are very mixed. There are blue points in the inside the red point zone. There are red points in the blue point zone. Like that, if it is there, then you can't draw the line. So what they are doing is they are applying a function which will actually move the feature points values in a way that the blue, all the blue go in one direction, all the red goes one direction. The blue and red classification is dependent on y. So basing on the y value, they are moving these x values. They're moving them, by applying a function. That function is called kernel function. Once they move them, and to a, in a way that they can actually, we can squeeze in a decision boundary there, that will actually help us in coming up with a solution which will help in either classification or whatever, right? So that's a good idea. I understand support vector machines better now. So kernel concept we understood to some extent. I am now very curious to understand those kernel functions more, but limitation of time, we can't go to that level of detail to understand each and every kernel function. But basing on the data segregation and stuff, because even though we apply a function, that doesn't mean the function's boundaries that it will create would not be linear always. It could be non-linear with a curve and all that stuff. So multiple ways is possible. So that's the reason they have multiple kernel functions that he has explained in the video and stuff, which is okay. But we didn't see important concepts called in the kernel support vector machines kernel functions. How do they calculate the loss, key thing, and basing on how do they reduce the loss, and then how do they fine tune it. Kernel functions are applied, and that will give us, so he said instead of going with x comma y for the training set to create the model, we'll go with f of x comma y. F of x is the kernel, but after coming f of x comma y, using f of x comma y, what kind of I mean, it should again be in somewhere, right? Like f of x gives us x1, x2, x3 again, but with varying values is my understanding. I should cross check on this. And this guy has explained the math. Longer video. Um, Definitely looks interesting, but I think we should spend more time on it on SVMs to understand the kernel's concept and stuff. The margins, soft margin, SVM, hyperplane, are the linear. So that first question, it's got answered. Like SVM hyperplane are need not be necessarily be linear. Kernel methods, we understood how they apply kernel methods, not to the detail, because there is a lot of detail in it on what he has explained and stuff on how they, why it is complicated to calculate it W in a linear regression, and how he's using kernel methods in place, and then how is he making the whole math easier by using the kernel functions, and what does he mean when xm is calculated multiplied with xn kind of stuff, and those kind of things are still little open questions for me, but still I think he has explained it, but maybe a little I didn't get a little um, part of it. So I'll try to spend more time to understand it, and then we'll discuss tomorrow. Soft margin SVM and maximizing margins. The so-called margining concept is definitely a good way to reduce the overfitting problem, and to globalize the solution with respect to model, which is very important concept that people should understand. But we'll get to it in detail tomorrow. That's it. Thank you for watching. Talk to you tomorrow.